Well, good morning. This is 8:05 on Thursday morning, the 22nd of June, 2017. It's supposed to be differential equations class, Math 238. Right now, I'm the only one in the room, so sorry that nobody's here, but we'll go on and continue where we left off last time. I'm waiting for the PowerPoint to open. Yesterday, about half the time, PowerPoint was extraordinarily slow. And this is just a three-page, screen file, so it shouldn't be very hard to open, but it does seem to take forever. So I should have had this done before. I forgot to open this before I started Screencast-O-Matic. Hate to waste recording time on something that's watching dots go across the screen. It is very slow. Yesterday, there it came up. Good. Okay, let's start the slideshow at this slide, and we'll be ready to go. All right, can't think of anything new to say now. We're on page 51, section 2.2, separable equations, differential equations. And here is a topic I don't think you run into very frequently, especially in the text, but perhaps in real life you might run into it more than you would care to, okay? And this is integral defined functions. I think I mentioned before that, all the stuff we're doing, learning these techniques and stuff like this, it's great, it's good, it gives you an understanding how they work and that type of thing, but in reality, most of the differential equations you'll ever run into are probably going to be non-solvable, okay? Or you might have to resort to something like an integral defined function or something like that. So let's pick up and go. Where this is coming from, if you remember, when you do have a separable function, usually it's f of g times, f of x times g of y or something like that. In this case, f of y and g of t or something like that. Let's just imagine that g is a continuous function on some interval I, that's an interval of interest for you, containing x sub 0 and the variable x. Okay, the I contains both of those things of interest. Then a solution of a simple initial value problem, here will be the form of these, dy, let me get my pen adjusted for black. Okay, you have dy dx is equal to g of x. That's one of the simplest of your separable equation. There is no there is no y dependence on the right hand side at all, so it's definitely not an autonomous differential equation, but this is strictly x dependence on the right hand side. So if you were, and by the way, the rest of this is that when y is evaluated at x0 at some point on the interval, you get a value called y0, just the classic definition or representation of an initial value problem, IVP. Okay, well, we know what to do. We write this in differential form. dy is equal to g of x dx, and then we integrate both sides, okay? And what you can do here, This integral comes out just y. And this integral over here, you're evaluating it, the limits on this, because you have a initial condition, you know that this is going, and I mean, you may not know this, but this is what you do. You put the x0 here and your variable x here, and then and because x is now being used there, you change, because inside the integral, that's really just a dummy variable. It's not really contributing anything. Change it to anything other than x and y, and probably d's or g's, you know, just so you don't confuse it with anything else. So they just chose t. That's usually their favorite, dt. Okay? Now, if g is integrable, that gives you some solution. But even if it's not integrable, it's still, that represents your answer, okay? With the condition that y of x0 is equal to y0. So let's plug that in. y0 is equal to the integral from x0, and then your x becomes x0, okay? G of t dt. We're plugging this in for the x, this in for the y, and guess what? That's just, yeah, that doesn't work, does it? Because that would be 0. So, belay that, okay. They just write it down without too much justification that this is y0 plus this, okay. I thought there would be a way to show why that's true. I'm not certain there is, okay. Well, they say the same thing I just said, but the right-hand side, left-hand side would have been a y0 then, with the right-hand side being 0, and that's not what they're saying, okay? Basically what they're coming down to, if this isn't an elementary function that you can't integrate, that's your answer, okay? Here's an example of that. Maybe this will make more sense, okay? That's sort of esoteric and without much, but here's one. dy dx is equal to e to the minus x squared, and y of 3 is equal to 5. Okay? All right. Now, number 1, g of x is a continuous function everywhere, from minus infinity to infinity. But its antiderivative is not an elementary function. You cannot integrate that. So basically what we do is this. I guess this is how they get around it now that I see their example. You're integrating, okay, doing something a little different now, okay? This time they're doing a dx here and a dx here. Now before, that wiped out your dx is here because it was now in integral form, differential form. But now we're going to leave that in there, okay? And this seems a little bizarre, but it's okay. But then when you integrate over x, okay, and since x is going to be in your integral from 3 to x, okay, you have to change the dummy variable to something else. They like t's. dy dt dt. Okay? And that was equal to integral from 3 to x of e to the minus x squared changes the dummy variable to be a t, not x. Okay? So that's e to the minus t squared dt. The right-hand side, not a thing you can do with it. Okay? But you can evaluate your at least they claim you can evaluate your trying to think. Initial condition, I couldn't think of the word. Initial condition from this. So what we're going to do here is, I still find what they're doing to be, okay, let's not do it yet. Let's just do the thing. Here's an integral of a derivative, okay? So that gives you y of t evaluated from t equal 3 to x. Over here, not a thing we can do, leave it as an integral. 3 to x e to the minus t squared dt. Okay. Now, let's plug in here, y of x minus y of 3 is equal to this. Plug in x equals 3 here, and you get 0. When you integrate from 3 to 3, any place to the same place, it gives you a 0. Okay? Well, I'm sorry. Maybe a step too soon. So let's go back in. Howdy! Good to see you. Tired of talking to myself. Because I've gotten into a really bad argument. No, I'm just, okay. All right. Projector bulb if there's no one to look at it. With the light, you can see better, you can see forward better. So, coming up slowly. We're on page, where we left off last time was on page 51, and we're doing example 5 at the bottom of that page. And this is when you can't, it's a separable equation, seems pretty nice, but when you separate it and go to integrate, no way you can solve that integral. It's not solvable. They call it a non-elementary function, okay? So you can't solve it. So what we've done, and this is a little different from before, okay? And it incorporates a couple of different things. Before, we wrote it in differential form, okay? Which is just dy is equal to e blah 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 dx, and then integrate both sides. And frankly, I think that would still work. I'm going to go back and redo it that way because to me, why change? But when you do integrate, and you see this keeps x being the variable that you're integrating over, but now this is like they did with fundamental theorem of algebra, with calculus, if you remember that. You can rewrite this with the variable here, but you have to change the independent variable there, because it's a dummy variable anyway. When you integrate it, it disappears, especially if you have limits. Okay? On this side it doesn't, that's still not integrable, but on this side it would. And what they do is y of t from 3 to x, when you evaluate that, because this is the integral of the derivative, which of course gives you the function. Those are kind of like inverse operations, so you wind up with the function you started with. Evaluate at x minus evaluated at 3. And this still gives you the integral you can't do anything with. So we'll write that down again. Okay? Whoops. I had my eraser on. So we'll write it down again. 3 to x e to the minus t squared dt. Okay? But our initial condition said when when x is equal to 3, y is equal to 5. So this then gives you y of x, okay, minus 5, because y of 3 is equal to 5 is equal to the unsolvable integral 3 to x. This time you're plugging in x equal to 3. So that would be 3 to 3 of e to the minus t squared dt. Okay, because you're plugging in for that. And of course, this, because you're integrating from the same, from one place to the same place, it's 3 to 3. This is really ugly. Okay, let me get that looking a little bit better. 3 to 3, goodness gracious, that doesn't look much better, does it? Okay, that's 0. So this says that y of that y0, and this, by the way, is your y0. Well, we already knew that. The constant here is 5. When I do not like the way they do this. Okay. Okay. All they do is just add 5 to both sides. Okay. So that will give you y of x is equal to 5 plus the integral, and go back to the x's now, of 3 to x e to the minus t squared dt. Okay. They went all around here to get that, which they had stated before. There's a part of me that this is very unfulfilling, because you're not really plugging in the value y of 3. You are substituting that. I mean, you're just putting that in. Now, let me go back and do it the way we did before, because it just seems bizarre that you have to do it the other. So let's try to do the same thing the way we did before. I think it'll still come out better, and to me, it's a little more satisfying. dy dx is equal to e to the minus x squared when, and your initial condition, y of 3 is equal to 5. The way we did it before was write it in differential form. dy is equal to e to the minus x squared dx, differential form, integrate both sides, and now, here's the little bit of difference. As x is going from 3, this is, because you're changing variables, I need to do it in the next step, okay? So this will be dy is equal to, since you're going from 3 to x, here, that's where you change your variable of minus t squared dt, okay? And here, when x is 3, y is 5, and when x is x, y is y, okay? Because y of x is, okay. So, I find this a little bit easier. I mean, makes more sense. This integrates to be y, and probably here you need to change your variable here too, so maybe I should do that, because you shouldn't have the same variable there. So make this a t. So this is going to be t evaluated from 5 to y is equal to, and you can't do anything with this or write it down, 3 to x e to the minus t squared dt, and that would be y minus 5 is equal to this integral, 3 to x e to the minus t squared dt. So this would be y is equal to 5 plus, add 5 to both sides, 5 plus, and that goes out, the integral from 3 to x of e to the minus t squared dt. You can't integrate that. So what you do then is do a numerical integration. You know, that's how you would come up with some type of solution to whatever accuracy you are striving to achieve. You just have to do that. We haven't done those yet, but we will. I think we did a little bit, maybe in chapter 1. I can't remember for sure if we did. I think we did. And later we'll mention another technique for doing that. Okay? But you can get packages that do those integrations for you. Okay. So, to me, this is not having to rewrite it and do using the same technique we did before. Now, there is a remark here. In some of the preceding examples, we saw that the constant in a one-parameter family of solutions for a first-order differential equation can be relabeled when convenient. The constant can. Also, it can easily happen that two individuals solving the same differential equation correctly arrive at dissimilar expressions for their answers. For example, by separation of variables, you can show that the one-parameter family of solutions for, I don't know if this is really worthwhile spending much time on, and it may not make you feel much better about it, but here's your differential equation. 1 plus y squared dx is equal, plus 1 plus x squared dy is equal to 0. Okay? Now, if you do this as separation of variables, this will be a 1 plus y squared dx is equal to a minus 1 plus x squared dy. Okay? And what I would do is divide both sides by 1 plus y squared, and also divide both sides by, and I think I want to do the minus, so minus 1 plus x squared. So this will wind up with a 1 plus y squared. This will wind up with a 1 plus x squared, a minus. Okay? And then what you have, these go out, those go out, these go out, and I'm going to swap sides. dy over 1 plus y squared is equal to a minus 1 plus dx over 1 plus x squared. Okay? And if you were to integrate both of those, what you see, if you recall, the antiderivative of this is the inverse tangent function. So inverse tangent of y is equal to minus the inverse tangent of x plus some constant c. And then if you add the inverse tangent of x to both sides, you got what they do in the book. You don't have your book with you, or do you? Okay, good. All right. Now, that's one way to approach it. Okay? Now, I don't want to actually do it, but I just want to show you this, that x plus y over 1 minus xy equal to some constant c. May be a different constant, I don't know. I wish they'd use two different c's if it wasn't. What if we take the derivative of that with respect to y? Okay? Well, that's the first thing I would do would be to multiply both sides of the equation by the denominator here, 1 minus xy. So this will be by 1 minus xy. And then that will wipe this out, and you would have, take the derivative of this, 1 plus y prime, which is dy dx. Maybe I'll should write it that way, just so it'll look more like a differential equation. The one we started with, dy dx, is equal to derivative of c is 0, and derivative of this, that's a product function, so it's going to be c times y plus y prime. Hopefully, you see, we're taking the derivative of both sides with respect to x. This gives you a 0. And this would be minus c. Okay? Now, it would be a minus c, I want to pull that out, times derivative of this thing. I pulled the minus out of that. And that's the product rule, so it would be derivative of this times that, plus this times derivative of whoops. Going too fast. X, y prime. Okay? Now, sorry. On the left-hand side, I had written y prime is dy dx. Let's do the same thing here. Dy dx. By the way, in my Cal 1 class yesterday, even though we had talked about it, I don't know how much, when I started using different notations, Leibniz versus the other and stuff, he said, but wait, aren't you? I said, no, those are the same. They are the same. Okay. So, let's solve for dy dx. Okay? So what I'm going to do is subtract, well, let's do this one step first. 1 plus dy dx is equal to minus cy minus cx dy dx. Okay? Now, let's get our dy's on the same side and the d and everything without a dy. So we'll be subtracting a 1 here, okay, and adding a cx dy dx here. So plus cx dy dx here. Okay. That goes out. These go out. Okay. So what we have here, combining like term, well, distributing out your dy dx, that will leave you a 1 plus cx. Okay. And that would be equal to a minus 1 plus cy. Pulled out the minus on there too. Okay? And then if you divide both sides by 1 plus cx, you get dy dx is equal to a minus 1 plus cy over 1 plus cx. Okay? Now if you turned around and wrote that I had not worked this out before because I just assumed they knew what they were talking about. That doesn't seem like that gives us the same differential equation at all. Not. So that's just a remark. Let's leave it alone. Okay, sorry about that. It sure doesn't seem like it's coming out what they say. And I think they left something out here. I can't figure out what it is, but I think they did leave something out. Okay. So anyway, homework exercise is 2.2, and the reason I do I's, they have the selected odd number problems answers are in the back, so that's what I give you. Any of the odds 1 through 21. Now there's a big bunch of them. I would do several of those. Make sure you feel comfortable about them all. Then any of the odds 23 through 27. Do 29. And do any of the either 31 or 33 or both. 35 or 37 or both, 39 or 41 or both, and I would do 43, it's the only one like that, and then any of the odds 47 through 49. Now the discussion problems usually don't have answers at the back. You can check and see if they do, and if they do, you might think through those. Okay? There's a mathematical model problem, which, since we don't have the packages they're talking about, you can still take a look at that and think through or work through as much as you can. No, I'm sorry, you might be able to do all that. It's the computer lab assignments. We don't have CAS, so you can maybe take them as the odds as far as you want to, but you might have to leave them be at some point. All right, so 2.1, we're looking at linear equations, okay? And just as a quick recap here, 2.1 basically dealt with solution curves without a solution, okay? From your mapping of the derivatives. Since you're in first derivative, that's all we're doing, first order differential equations. You can write that derivative as a function of your variables. And in the process of doing that, they, in fact, almost exclusively focused on autonomous differential equations. And the key thing about that, I mean, they did some with the direction field without it, but then the bulk of the rest of it was with that. And that means that when you have your dy dx, isolate the other side, it's only a function of y, that's an autonomous. And they dealt with that then. 2.2, separable equations. Okay? And as we saw, some autonomous equations, in fact, I would say every autonomous equation is separable, and but not all separable, but some separable equations are also autonomous. In fact, they're basically the same things. Okay? But you can have functions of x you can separate. So let's move to then a new class, and this class is called, I meant to hit the erase key and I hit the stop key. Okay. Not what I wanted to do. Okay. Linear equations. Linear differential equations are a especially friendly family of differential equations, and we'll leave that definition for friendly to your discretion to see how friendly you think they are. It says that they call them friendly in that given a linear equation, whether first order or higher order, okay, there's always a good possibility we can find some sort of solution of that equation that we can examine. That's not saying a lot. It's blah, blah, blah. Okay, here's the definition for the form of a linear first-order differential equation that was first given back in equation 7 in 1.1 when we were talking about linear versus nonlinear. In this form, in the case of n equal 1, in equation 6 of that section, is reproduced here, and here's that definition. First order differential equation of this form, a1 of x, that's some coefficient function of x alone. No y's in it, but there could be x's there. Multiplied by dy dx plus some other function, a sub 0 of x, that coefficient function is a function of x alone, but then you have the y term there, y multiplied by it, okay? And that's equal to some g of x, okay? Which is, again, a function of x alone. Now, what makes this linear is the fact that the first derivative is to the first power, and the y is to the first power, okay? Now, and you got your y's on this side and things that only have x's there. A sub 0x and a sub 1x only depend on x. but they're part of this other thing. They're the coefficient for the first derivative and the coefficient for the y. Okay? Now, would you think, okay, so definitely not autonomous. With autonomous, you can isolate the dy dx, and on the other side is going to be a function of y. No way. G of x is not a function of y. Okay? It's a function only of x. So it's not autonomous, can't be autonomous. Okay? Is it separable? Well, no. Okay? If you wrote it in differential form, this dx would then show up here and here. So basically what I would do before I did that was subtract this from that side, and then write it in differential form. And even though you can divide out the a sub 1 of x, you still got the a sub 0 of x and the y coupled in a way you can't separate. You cannot separate. Because, number one, this is subtracted from g of x. You can't factor out the y because the g of x has no y in it. So this cannot be solved separately. Okay. So this is the most generic form of what we call a linear equation. Many of them will be much simpler than this. Okay. It could easily be this function right here is just a constant. Okay. The a sub 1 of x. Right? Could be this is just a constant. Okay? It could be that this is just a constant. Do you see it? It could be this number is just, this function is just a constant function without x dependence. That's going to make life a little easier. It could be this one is a constant without x dependence. And it could even be that's a constant. Now, this constant, the a sub 0 of x, and that one, either or both could be 0. This one can't be, otherwise it would be a differential equation then. So we will see this in much simpler forms than this, but this is the most generic form. Notice no y dependence here. The only y here is to the first power. Everything else is a function of x, and this is only a function of x. So this we call a, and by the way, x's can be to any power you want to. They could be sines, trigs, exponentials, logs. They could be to the 15th power. They could be all that stuff. The y can't. The y can only be y, okay? And the dy dx can only be dy dx. Can't have any other y dependence here, y prime dependence there, anything other than a linear function in y. Not in x, but in y. Okay. That's said to be a linear equation in the variable y, because this is to the first power, that's to the first power. The x can be anything. Okay. Now, first thing we're going to do with this is this. Divide out this coefficient. a1 of x. a1 of x. a1 of x. Okay. Now, that's gone. So now we have dy dx, and this is what I was just talking about, that you could have that coefficient being a constant, and the constant could be 1. This is the way to get there. Plus, now, these two are functions of x, only of x, so the quotient is a function only of x. We're going to give it a new name. We don't like a1 and a0. We're going to give it a new name, p of x. Okay? Now, the y stays y. Now, this function is a function of x alone. It may be a rational function. It may not. The a1 of x could be a constant. So, whatever it is, let's give it a new name. Well, how about f? Okay? F of x. So, this is really another way to express a linear function in y. Okay? And again, this is to the first power, that's to the first power. But now you've limited it to two functions, whereas you had three here. If you had that, divide out this. This is a function of x, a coefficient function here. Divide it out. It may make these really miserable looking functions, but fine, you're better off with that than to have something out here. So here's your first step. If you had something like that, come up with something like this. Now, it says here in some instances this could be solved by separation of variables. Okay? For instance, if this p of x was a constant, correct that. Man, I can't think of many that you could. You would have to, of course, add this to that side. Okay. If f of x was a constant, okay, that would work. If f of x was a constant, can't be a function of y, it would be a linear function. Can't be a function, it could be a constant function. So if that was a constant function, then subtract this from both sides, okay, and you'd have c minus p of x y. Yeah, I don't know. I'm not certain I will buy that. Let's take a look. Okay. Here's their examples. dy dx, fine, plus 2xy, fine, is equal to 0. Okay. That's what I didn't think of. I said if f of x was a constant, that constant would have to be 0. Okay. Now we're okay. Because what we would do is subtract the 2xy from both sides, then write it in differential form. Dy is equal to 2xy dx divided by y. Yes, that's simple. So the only way I was getting there, I said f would have to be a constant. Not only any old constant, it has to be the 0 constant. 0. Okay. Then that's separable for sure. Okay? So you see linear functions can be separable too. In really special cases. Okay, let's look at another one. dy dx. I'm going to not write it the way they do. Minus y is equal to 5. Okay? In this case, both the p of x and f of x are constants. Okay? Now, what you can do here is add y to both sides, which is where they start. And that would give you dy dx is equal to y plus 5. And then write it in differential form. Dy dx, I'm sorry. Say write it in differential form or write it in derivative form. Okay. Okay. Dy dx. And let me go on and divide by y plus 5 is equal to dx. Yeah, separable. You can do it. Okay? What's even more true is that's also an autonomous function, isn't it? When you get it in that form right there, dy dx is a function of y alone, no x dependence at all. So, these two circumstances, a linear function can be separable or autonomous. Okay? So, you can still do it. Most of the times your linear functions will not be either of those, but you could. If you got them, use them. Okay? But this one, dy dx, very simple looking function, plus y equal x. Can't get much simpler than that. Guess what, team? Not separable. Not autonomous, okay? This is only linear. These are the kind we're going to be focusing on now. The others will work too, and we'll do some of those, but we'll be focusing on those that you can't do anything else with, okay? That's not separable and certainly not autonomous either. So, let's go back to the original. So let me erase all this. And here's our original. Our second original, okay? When we write it in this form, dy dx is equal to some p of x, y. No. Okay. Goodness, my nose is itching. Plus p of x, y is equal to some f of x. That's what we got it down to. If you had that coefficient of your y, whether it's a constant, whether it's a function of x, it just can't be a function of y, of the dy dx, divide it through and get into this form. Once you're in this form now, okay, this seems like a bizarre way to go, but it works, okay? This method of solution hinges on solving that equation it hinges on the remarkable fact that the left-hand side of that equation can be recast into the form of an exact derivative of a product by multiplying both sides of that equation by a special function mu of x. Okay? And then it says it's relatively easy to find that mu of x. Okay? So here's what we're going to do. Okay? We're multiplying both sides of the equation by mu of x. When you multiply this by mu of x, okay, you have, no, they're jumping to their solution now. Okay, sorry about this. Here's something to note. Just think of this. We're going to multiply a y by mu of x. Let's do that. Mu of x times y. Right? Now, we're not doing what they said yet. We're just doing this. What happens if we take a derivative of this? D by dx of that. You remember the product rule? Okay, so what would this give you? Mu of x, y prime. Remember, you're taking with respect to x, so that would be your dy dx. And I probably shouldn't mix my notations like this. Let me write this as dy dx. Okay. Okay. Plus, and then the other half of the product rule says, okay, I guess I'll write that d of mu of x dx times y. Okay, and that's what they show here, mu dy dx plus dy d mu dx y. Okay, now, okay. Now, if we had multiplied, okay, notice here. Here's the key. Okay, if we had multiplied this by mu of x, this by mu of x, and this by mu of x, which is what they said we were going to do to begin with, notice something here. This thing right here is exactly that term. Okay? Now, this term right here doesn't look just like this unless d mu of x dx is equal to p of x times mu of x. If those are equal, then this would be exactly that. Okay? Now, what does that mean? Okay? If that term were this, okay, exactly, okay, now they leave off the of x's to make it look a little simpler, so let me do that. D mu dx is equal to p mu. Mu p, they'd say. Doesn't matter which order. Okay. Now, seems bizarre. It seems like we're going around your elbow to get to your ear and you still don't know where you're going. Okay? But remember that this p is a function of x alone. So this is now a separable equation. You can say d mu over mu is equal to p dx. Okay? You've just sort of lost your y's here, but not really. We're going to come back and plug that in. If you were to integrate both sides of this gives you, what's the integral of d mu over mu? Log mu. Okay? And technically it should be an absolute value. Let's just assume mu's always positive. Never zero, never negative. We may live to regret that, but let's try it. And then this would be the integral of p dx. Now we don't know enough about p or anything to know whether we can do that. But how do we isolate this mu here? How do you undo a log? Exponentiate. Okay? So this would give you mu is equal to e to the integral of p dx. Remember, p is a function of x. Hey, guess what? Every time you do that, you're going to make this function into something that is a derivative of a product. A perfect derivative of a product. Okay? So let's back off and see exactly what we should do here. Okay? This is the key for these linear differential equations. This is how you start. You get the form into dy dx equals p of x times y, plus p of x times y is equal to f of x. Get it into that form by dividing. If you had any coefficient here at all, any coefficient here, divide it and get it into this form. That's pretty easy to do. Okay? As soon as you get it and I've identified what this p of x is, then integrate that p of x dx. Okay? As soon as you get that, if that's a elementary function that you can integrate, and most of them are, okay, then you get some answer there. Then use that as the exponent of mu. That's going to be your mu. Okay? Mu is going to be that thing. So integrate this, then exponentiate what you get as your result. That's going to be your mu. Okay. All right. Seems bizarre, but that's what. And we call this the integrating factor for that differential equation. Okay? Okay. Now they do a lot of writing out of a lot of mess here. And then they say, don't memorize this. Okay? So why go through all that? Okay? So here's the steps again. Remember to put the linear equation into standard form, which is the dy dx by itself. Divide by whatever's in front of that. Secondly, identify that p of x that you have that is the coefficient of y. Integrate that dx, and then whatever that turns out being, that is the exponent of e. Okay? Now, when you're doing that integral, don't insert a constant. Just leave it alone. We'll get to the constants later. Okay? Now, once you have that integrating factor, that mu, which is e to the integral of that, multiply both sides of that by that integrating factor. And then as soon as you do that, you have a perfect derivative on one side, and you have this result on the other side. Then you integrate both sides. So, a lot of blah, blah, blah. Let's go back and do that. Okay? We're going to start with a very simple one. Okay? dy dx minus 3y is equal to 0. Now, remember, this is a very simple one. Would I do this doing integrating factor? No, I wouldn't. I would do separation of variables. But since this can be done either way, let's do our integrating factor and see what we got. Okay, number one, you check. Is your coefficient of your dy dx 1? Yes, it is. Nothing else needs to be done there. Second, identify your p. P of x is negative 3. That's pretty simple. So what we do with that? We integrate minus 3 dx. That's the first step. And what does that come out being? You may have said it, I can't hear. Just integrate. We integrate that p of x. Second? No, it's just 3x. Yeah, minus 3x. Because you have the minus sign out in front. Because the integral, okay, I should have done this. I should have put the 3 out there. You're integrating dx, it just gives you x. So minus 3x. And what do we do with that? We make that the exponent of e. Right? This is now your integrating factor, mu of x. What did it say do with that? Multiply it by everything on both sides of the equation. So here we have a e to the minus 3x dy dx minus 3 e to the minus 3x y is equal to 0. Because you multiply that by 0, it's still 0. All right. By that? Now, supposedly, and it is, okay, this should be the exact derivative of the product of these two functions, e to the minus 3x and y. Let's just check that and make sure that's true, okay? Let's just check it and say e to the minus 3x times y. What happens if you take the derivative of that? Derivative of that with respect to x. That would be, do the product rule. Yeah, you start with the first one, e to the minus 3x dy dx, right? And then you would do a plus y times derivative of this, which would be e to the minus 3x, chain rule times a minus 3. So that changes that sign to a minus and puts the coefficient of 3 there. Right? Now let's see. Yep, that's exactly what we've got here. Okay? Exactly. So therefore this thing here is that. Okay? So we're going to do that. We're going to replace this with d of e to the minus 3x times y. You might want to put the y in front so it's better. It doesn't matter, but I like it better that way. Is equal to 0. Okay? And then I know this is a separation of variables, but you can still integrate both sides, can't you? Okay? Integrate that, okay? Right? You integrate a perfect derivative, which is what this is, right? So perfect derivative, integrate that, you get the function, okay? So your answer here is going to be e to the minus 3x times y. I'm going to move the y in front. You integrate 0 and you get what? A constant, exactly. And guess what, folks? That's your solution. Now you could write it this way: y is equal to c e to the 3x. Okay? There's your constant of integration. You need one because it's a first order equation. And let's see if that works. Let's go back to our original equation and do a dy dx. Right? And what would that be? Take the derivative of that. Of this. Dy dx. Say again? Well, c is a constant, so just do the constant multiple rule. C times is not a negative anymore, e to the 3x, but chain rule gives you a 3 there, right? Okay? So, there's your dy dx. So let's do dy dx, which is 3c e to the 3x, minus 3 times y c e to the 3x. Guess what? Sure enough, that's equal to 0. So that is a solution. It's a family of solutions. You choose any c you want to. It's still a solution. And we've just shown it is indeed true. Now, would I have gone through that to solve this one? Hopefully not. Okay? Hopefully I would have done this. And if you don't mind, I'm going to erase just a little bit of it up here. I hope I can get everything written in that space. I would have written this as dy dx is equal to 3y, right? And then I would write that in differential form, which would be dy, and separate the variables. Dy over 3y is equal to dx, right? Okay? Then I would integrate both sides. I'm going to pull out the constant 1/3, okay? Integrate this, and that would be 1/3 integral of dy over y is this part here. Yeah, integral of 1 over y dy, yeah. ln y, exactly. ln y, okay, and integral of dx is just x, okay? So what I'm going to do is multiply both sides by 3, wipe out that, and then exponentiate both sides, and you get y is equal to c, okay. There's a constant there, c e to the 3x, okay. You have to do a little bit of manipulation to get the c in the right place, but yeah, same answer you got there. Easier doing separation of variables, but you see it works either way. This is a linear equation. A very simple one, and that the p of x is a constant and the f of x is 0. You can't get too much easier than that, but we got it. Okay. And that, by the way, that's good for all values x. Your interval can be all real numbers x. Give you that. Okay, ready to do example 2? All right. Got to find my cursor here. dy dx minus 3y is equal to 6. That looks a lot like the last one, except now you have a constant there rather than 0. Okay? But you know, I don't think too much has changed, because the left-hand side is exactly what it was before, right? And that's all we dealt with to begin with. Where do we begin? But let's go through the steps just to make sure. First, identify. Let's go through all the steps. First, make sure your coefficient of the derivative is 1. It is. Secondly, identify what your p of x is. It's still minus 3. Okay? And then what do we do with that p of x? You integrate it. Integrate of minus 3y. I'm writing it that way this time. And what is that? Dy minus, wait a minute. I'm sorry. Goodness gracious. Not y. Okay. The p of x, okay, which is just minus 3. Okay. Minus 3 dx. Okay. That be minus 3x. Okay? And then what do we do with that? Write it as the exponent of e. Okay? That is now your mu of x. Okay? So I'm going to multiply that by both sides of the equation. E to the minus 3x dy dx minus 3 e, I'm going to put the y in front. I don't like it behind. Minus 3y e to the minus 3x. Okay? Goodness. I've had, over the weekend, I got a little bit of conjunctivitis in my left eye. And the last couple of days has been really good. But this morning it woke up really itchy, which is how it usually begins. So I put drops in it, and now it's driving me nuts. And what I've noticed after about an hour, hour and a half, something like that, of looking at the screen and the light and stuff like this, it just seems to be so light sensitive. It's just driving me nuts. Okay, and this we notice is d by dx, okay, of your integrating factor e to the minus 3x times your y. And there I wrote it in that order again. Okay? And that's the same thing we had before, right? So we don't have to go back and check that. So what we have now, this thing here, the one other thing we didn't do is when we multiply both sides, before it was a 0 there, now it's a 6. The 6 also has a e to the minus 3x by it. That's the difference in this problem. Okay? So here's what we've got on the left-hand side, and this is equal to e to the minus 3x, 6e to the minus 3x. Goodness gracious, I wish that would quit hurting. On the right-hand side. Okay? But the good news is that's still just a function of x. It has to be, right? The f of x has to be a function of x alone. The use of x is a function of x alone. Sure, we can still handle this. Now we just do separation of variables. Well, no, not quite. We integrate both sides, okay? Don't do separation of variables. You can't because it's not separable. But this is a perfect derivative. So what you get here is e. I'm going to put the y in front. Y e to the minus 3x is equal to, and integrate this with respect to x, and what do you get? Say a little louder. Yeah, and in fact, let me do this to make it maybe a little easier. Okay, when you put the integral sign in, put it in between the 6 and the other, so that's a little easier. So this will be 6 What's the antiderivative of e to the minus 3x? E to the minus 3x over a negative 3. You unchain rule it, kind of, remember? Okay? Before the chain rule was getting you, now the unchain rule gets you. Okay? So this is going to make this a minus 2. Okay? This is going to be minus 2e to the minus 3x. Okay? So here's what we've got. Y is equal to, y e to the minus 3x is equal to minus 2e to the minus 3x. Oh, wait a minute, folks. And by the way, we did have a plus c here. That's where you put in your constant. So we have a plus c. And what you do is multiply both sides of the equation by e to the positive 3x, right? So that will be y is equal to negative 2 plus c e to the 3x. Okay? So this answer looks a whole lot like the other, except we've got a minus 2 in front. It's not an arbitrary constant. It is a constant of the problem. Now, if you're a little suspicious of whether this really is true, why don't we take a derivative of it? So let's do it. dy dx, we're trying to reproduce this now. dy dx is equal to, of course the negative 2 doesn't contribute anything here, that would give us, see if you agree with this, 3c e to the 3x. Agree? Okay. And then your minus 3y is going to be 6 minus 3c, 3c e to the 3x. All we did is multiply the minus 3 here by the y up there. Okay? Now we combine those together like they are here, and that would be 3c e to the 3x. And we did minus 3y, so this is plus 6 minus 3c e to the 3x. Is that equal to 6? Sure enough, it is. So, absolutely, that was our solution. So that solution is minus 2, y is equal to minus 2, plus c e to the 3x. And that's, again, good for all values of x, anywhere. All right, now you do have a book, you can see the figure. Okay, if you'll look at the, I'm just holding up, not that this will be projected, I mean it's not projected, so it's not going to be stored. I'm just doing here, this is that family of curves. Solution curves for this differential equation. Okay? Especially when I stare at this brightness here. Okay? And it's c, I can't see. Oh, y is equal to minus 2, that's when, I can't say, okay, right here. That's when c is equal to 0. So when c is equal to 0, you have just the solution y is equal to minus 2. Okay? So that's when c is equal to 0. And these others are other values of c. Negative 1, blue's negative 1, blue's negative 1, the red is positive 1, the green is 2, the yellow, my eyes are hurting so bad I can't make this out. No, that was just the scale. That was just your X scale. Sorry about that. They don't indicate what C values those are. But I know that the dotted blue line there, y is equal to negative 2, that's when C is equal to 0. And you pick other C's, and you get curves that do like this. My guess, when when C is equal to, let's say, plus 1, it'd be minus 2 plus e to the 3x. So, right? Okay. You see what the minus 2 does for you here, it translates it downward, okay? If you were to translate this thing upward, in other words, get rid of the minus 2 up there, then this first one would be an exponential function, okay? For any other values of C, that is a horizontal stretch, okay? Because it looks like to me a horizontal stretch. But anyway, if C is positive, you have the ones up here, and if C is negative, you have the ones down here. Okay? And so that I think is a better description of it. Sorry, I can't see it. But anyway, you probably were interested in that. Anyway, now, the concept of a general solution is what they approach next. Suppose again that the function p and f in our original setup, let's go back to that. Okay, remember what it was? dy dx plus p of x y is equal to f of x. Okay? And that's my eyes are driving me. I'm not supposed to rub them or scratch them, but it's just is driving me nuts. I can't touch them. Okay. Suppose again that the p and the f here are continuous on some common interval I. And the steps leading to 4, which was how we came up with our solution, which we don't ever use that form, okay? We showed that if 2 has a solution on I, then it must be in the form given by 4, okay? Okay? Conversely, it is a straightforward exercise in differentiation to verify that any function of the form given in 4 is a solution for the differential equation 2. So it goes both ways. In other words, 4 is a one-parameter family of solutions for 2, and every solution of 2 defined on that interval I is a member of that family. Therefore, we call that 4, which we said don't memorize, okay, that really, it looks complicated when you write it, but when you really do it, it's a lot simpler than that. That's your general solution. So when you came up with the end, that is a general solution, okay? And they talk again about going back to remarks at the end of section 1.1 when they talk about general solutions. Now by writing 2 in the normal form, y prime is equal to capital F of xy, we identify that capital F of xy is your minus p of xy plus f of x, because you just subtract this from both sides and that's what you get, okay? From the continuity of p and f on the interval, we see that f and the partial of f with respect to y, wait, I'm sorry, I skipped a line. Identify that f is that, and the partial of f with respect to y is minus p, okay? Because if that capital F of xy is equal to little f of x minus p of xy, then the partial of f with respect to y is going to be, that has no partial, because there's no y dependence in little f. So this would just be minus p of x, okay, and that's what they got here, right? From the continuity of P and F on the interval, we see the F and partial of F with respect to Y are also continuous on the interval. Now, with theorem 1.2.1, which a long time ago, I don't even remember what it was, we conclude that there exists one and only one solution of that first order differential equation with those initial values, okay? Because once you put an initial value in, you don't have a family anymore, you pick that one that fits that, okay? Defined on some interval I0 containing x0. But when x0 is in I, finding a solution of 6 is just a matter of finding the appropriate value C, which that's exactly what we do when we do initial conditions. So it seems like a lot of blah, blah, blah to something we were pretty straightforward on. In other words, the interval I0 of existence and uniqueness in that previous theorem for the initial value problem is for the entire interval I. Pretty esoteric thing they're dealing with. Let's go to example 3. I'm tired of those. Well, what if, you know, and if you did this, do exactly what you expected to. So here's another one. X dy dx minus 4y is equal to x to the 6th e to the x. Questions for you. Number 1, is that a linear equation? Oh, huh?
Is it an ordinary equation?
Okay, it is an ordinary, those are not partials. Okay. I said, is it a linear differential equation? Why not? Okay. And I should have said linear in y. Yes, it is. Because the dy dx is to the first power and y is to the first power. The only y's you have, they're all to the first power. That's when in y, not in x. Okay, obviously. Okay. Now, is it in our standard form? Why not? Yeah, you have an x as a coefficient. It is linear. That can have a coefficient of x. How do we get rid of that? Divide everything by x. Now, they're not going to mention it now, but if I know them, they're going to bring it up later. Divide this by x, divide this by x, and divide this by x. Okay? Now, time out. Okay? If x equals 0 was a solution, by dividing by x, you lose that. Because you can't ever divide by 0, right? So you have to keep that in mind. If x was and then that is going to be one of those, what do they call them? Not special cases. We talked about that last time. When you lose a solution, that is called a yacht. Where are they not saying it? Let me go a little bit further back. Well, I can't see it. Yeah, I know we dealt with it because I thought they went on to it in an obnoxiously long and complicated form. Yeah, I don't think I dreamed it. We really did do it. Here's an example of it. I just can't find the word. And it hurts my eyes to strain for it, so I may just give up on this. singular solution. That's what I was trying to remember. Because we divided by x. Now, it may be x equals 0 will not be a solution for that, okay? And if it isn't, fine. But if it was, we just lost it, and that would be a singular solution. So let's just look here and see if maybe it would be. I don't think so. But you can't tell. I can't tell just looking. All right, let's see what the new form, standard form of this differential equation would be. What would it be now? I'll do it over here. dy dx, that's what we wanted by itself alone, no coefficients except 1. So that's fine. Second? Minus 4 over x, that's your, times y, is equal to x to the 5th e to the x. That is now in our standard form. And where do we begin once we got it in standard form? Identify your p of x. And what is your p of x? Negative 4 over x. And what do you do with that p of x? Second, integrate it. So the integral of minus, I'm going to put the 4 on the outside, dx over x. You agree that's what okay. What would that be? Yes, minus 4 ln x. Okay? Good. Now, obviously, x can't be 0 here, okay, because you can't take the ln. So if that was a solution, you're not going to come up with it here, okay? So, what do you do with that then? Second, raise it to the e. Before I do that, I'm going to write it in a slightly different way. That's the same as log x to the minus 4, isn't it? Remember that rule of logarithms? Okay. Now I'm going to raise that to the e. Why? Because I wanted a ln by itself. And what does this give you? X to the minus 4. There is your integrating factor. That's your mu of x. Right? Mu of x, okay? And what do we do with that? By everything on your standard form. So this will be x to the minus 4 dy dx minus, okay, you got a 4, and that was already x to the minus 1, times this will be x to the minus 5. So, I don't know. I'm torn between which way I want to write it. Let's keep it in negative x1. X to the minus 5, okay? Y, why not, is equal to, and when you multiply x to the minus 4 by the right-hand side, what are you down to? Second, multiply x to the minus 4 times the right-hand side. Multiply that by x to the minus 4, and you get x e to the x. Very good. Now, if everything's worked out like it's supposed to have, which I hope it has here, this should be d by dx of a product. And that product should be x to the minus 4, y x to the minus 4. Okay? Now, because I'm a cynic, I'm always worried that I may have done something wrong. I want to take that derivative now just to check and see if we get this. Okay, when I take the derivative of the first, you get dy dx times the second, x to the minus 4. Good so far. When I do the first times the derivative of the second, it's going to be a y, fine, times the derivative of this will be a minus 4 x to the minus 5. Yes, that works. So I feel pretty good about this. Okay? And that perfect derivative is equal to x e to the x. So that means if I integrate both sides of this, and I'll need to put a dx here, okay, then my left hand, and technically I am putting a dx here too, they wipe out here, and then you're doing the integral of a perfect differential, and you get exactly this. So you get y x to the minus 4 is equal to, can we do this integral? Say again? How? Yes. What's that? Not product rule. Actually, the technique comes from the product rule. Huh? Not the chain rule. Stay with product rule. It comes from that. Integration by parts. That's it. That comes from the product rule. Okay? Now, parts is parts. What part is what? Let u equal x and dv equal the rest of it, e to the x dx. Okay? Now, here's what the integration by parts wants you to do. Pick the one that when you take the derivative, that's going to be the next thing we're going to do, it gets simpler. But when you integrate this, it doesn't get any worse. And sure enough, e to the x doesn't get any worse. So you get simpler here when you take a derivative. When you integrate here, it doesn't get any worse. So that's what we do next. We then, du is equal to dx. That's just pretty straightforward. And when you integrate this, you get v is equal to e to the x. Yeah. Because when you take dv, it's dv dx. E to the x dx. So that's fine. So what do you do next in the integration by parts? Yeah, you multiply the u times the v. So this is going to be x e to the x. And then what's the next thing you do? Minus the integral of v du, the bottom line here. And that integral is pretty simple. E to the x dx. Right? Right? Okay? And what is the integral of e to the x dx? Huh? E to the x. So that'd be minus e to the x. So here's what we've got. Oh, plus c. Okay? Don't forget your plus c now. We've been ignoring it for a while, but don't forget it. So here's what we've got. Y x to the minus 4, that's what you get when you integrate this, integrate a perfect derivative, okay, is equal to x e to the x, that was the first part of this, minus e to the x, that's the second part, plus c. Now that might not be the best way to express it, but it's okay. So what we're going to do then is multiply to isolate the y, multiply everything by x to the 4th, right? So that'll be y is equal to x to the 5th, e to the x, minus x to the 4th, e to the x, plus c times x 4th. All right, there's your constant embedded in the thing. If you had any doubt, you could say this, but if you did, you could take the derivative of this. It's not that bad. So let's do it. Okay. Well, I say it's not that bad. Dy dx. This is just checking. This isn't necessary, but just if you want to make sure you got it right. Then however you want to do that. I'm going to go in and do derivative of the first. 5x 4th e to the x. That's the first half of the product rule. plus x to the fifth e to the x, that's the second half of the product rule, minus 4x cubed e to the x, minus x to the fourth e to the x, two product rules there, and then the last is just plus 4x cubed, 4c x cubed. Okay, didn't allow enough room, but I think I got it all in there. Okay, the second part, oh wait, the original equation had an x in it, so we need to multiply this by x. Okay, so that x then would be, make this x to the fifth, make this x to the sixth, make that x to the fourth, make that x to the fifth, and make that x to the fourth. Okay, I'm rapidly running out of room. Okay, so I'm going, okay, let's just do the next part. Minus 4y would then be minus 4x to the fifth e to the x minus, oh wait, plus 4 x to the fourth e to the x minus 4c x to the fourth. Okay? Now, I'm going to take those two things. Got to erase a little room for me up here. Okay? I'm going to take those things and add them together. Okay? Now let's see if I can help myself out a little. There's 5x to the fifth. Okay, wait. Time out. Most of these terms have e to the x in them. So let's factor out an e to the x for those terms. Okay? Now let's see what we got left. 5x to the fifth plus x to the sixth minus 4x to the fourth. Oh, there's another x to the fifth, right? So it was 5 minus 1, so that's going to be 4x to the fifth. That'll take care of this one and that one. And then here we've got a plus x to the sixth. Can't do much with that right now. Okay. And here we have a minus 4x to the fourth plus 4c x to the fourth. That's going to be a minus 4 minus c. I'm going to write it that way. Okay, x to the fourth. Okay, that's the that's the dy dx term with the x multiplied in. Okay, then the minus, okay, wait. I almost blew that. Let me back up just a bit here. These terms here, the last two, wait. Okay. I almost blew it there. That last term didn't have an e to the x in it, so this is just a minus. Let me get rid of that parentheses too. That's why I hesitate to do these, because they're so tedious. Okay? We're doing those with the e to the x terms, and we got those, and this one is by itself, minus 4x to the fourth e to the x, and then we have the plus 4c x to the fourth. That one didn't have an e to the x in it, so we can't combine it. Okay? Now let's do the same thing with our minus 4y part. Okay? Again, you have e to the x's by a bunch of these, and the first one here is going to be minus 4x to the fifth. The next one's going to be plus 4x to the fourth. And then out here, those are the only ones that e to the x is it. You have a minus 4c x to the fourth. Look at that. Okay? So this term goes away, that term goes away, that term goes away. What do we are left with? X to the 6th, e to the x, and that's the right-hand side of your equation. Yes, it works. Now that checking is almost so tedious, you could be more likely to make a mistake there than you would in solving the problem. But if you're careful with it, you can check it and see, yes, that does work. All right, so that was your, okay. Why didn't I look down this page? What did we do to that problem that could have produced a singular, as in x equals 0? Well, that's what we did. When you divide it by the a sub x, anytime that makes a 0, that could be a singular point. Okay? But one other issue here, let's talk about our interval. By dividing by 0, we excluded 0 from the interval. And then when we see that doing right here, that excluded all negative x's. So in this one, automatically your x's have to be greater than 0. Not greater than or equal to 0, greater than 0. Can't be 0 here, and neither can it be 0 here. So that excluded those. If there are any solutions that would be in a negative number or 0, those would be singular solutions. They're not part of your general solution. Okay. Oh, man. How did this happen? We've only got, 2 minutes left? I don't think we can get example 4 done in 2 minutes, not judging by example 3. So let's pick up with example 4 next time, which means let's look for some homework exercises here. I think you can do any of the odds 1 through 23. There's a whole bunch of those. Now, we didn't do any with initial values. Yeah. So let's hold off the rest of those until next time. Okay? What's that? 1 through 23. You don't have to do them all, but do some of those. All right. The other thing, yeah, I think that's it. Okay. I guess the other thing is